Hey everyone, so here's the next set of problems. This is all dealing with projectile motion, some horizontal and some vertical. All right, here's the first one. Pause the video, work itself. Let me go in a second. All right, so they want us to figure out what change we can make in order to increase the time that the ball is going to be in the air. And the one thing to keep in mind is that there are two dimensions, x and y, that are independent of each other, and any changes in time must be done through a change in the y direction. Changing something in the x, like making the muzzle go closer to the edge of the cliff, or giving the ball a greater horizontal velocity, will not affect when the ball lands, it affects where it lands. So in order to change when it lands, we have to either change the acceleration, which is going to be impossible, change the initial position so it's more vertical, or increase this so that it shoots upwards at an angle. So if we're changing the initial velocity in the y direction, the height in the y direction, or the acceleration in the y direction, those would affect the time. The only choice here would be positioning the cannon higher above the ground. Okay, here's the next one. Pause video, works up. I'm gonna go over in a second. All right, so they want us to figure out what's going on. We have we have a player throwing a ball horizontally, and they want us to figure out kind of what happens to vertical speed and horizontal speed. So right off the bat, in the x direction, we know that there's no acceleration. Therefore, the v is going to be constant. So what I can do is, this one says it's constant, this one says it increases, so b's out. And here it says the horizontal speed increases, so that one's out. So choices are now between A and C. Now what happens with the vertical speed? Well, it starts off 0, but because there's a vertical acceleration, it's going to end up falling down and increasing in speed. So the answer would be C. The vertical speed increases because of the downward acceleration, and the horizontal speed remains the same because there is no acceleration in the x direction. All right, here's the next question. Pause video, work yourself, and we'll go over in a second. I apologize if you couldn't see this fully, but you do have a copy of what these questions look like. Uh, Basically, the main way that you have to approach this is by doing an XY chart, writing down all the given information. I'm not going to write it all out completely. I guess I will actually. So I have all my unknown variables. I have my given pieces. This is actually supposed to be a y, not an x. So the initial position in the x direction, we usually say that this is 0. We're trying to figure out what this is. The initial velocity, this 25, is only in the x direction, and that remains the same because the acceleration is always 0. In the y direction, the acceleration is negative 10. Because it's being thrown vertically, that means it has no initial velocity. It starts off above the ground, so it starts off with an initial position of 45, and when it reaches the ground, we're going to say that the ground is 0. So this is what we have for that. Now, remember that in order to use the x column for anything, we have to have every term in there. We're missing two things, the final position and time. So in order for me to find the final position, I have to find the time. So what I'm going to do is I'm going to look at the y column and use this in order to find time. So I use the annoying x equation. So it's going to be 0 equals 45 plus v naught t plus 1 half a t squared. Move some things around. So this ends up being 5t squared. Bring it over to the left side. We have the 45 over here. Divided by 5. We end up getting that time is going to be equal to 3 seconds. Once I have that time, I can now essentially use the annoying x equation again, this time using the x column. Uh, the only thing of worth is the fact that the initial velocity is 25. So we end up having 0 plus 25 times 3 plus 0 for the acceleration term. And that ends up getting me the distance to be 75. All right, here's the next one. Pause the video, work itself, and we'll go over in a second. All right, they want us to figure out the height of the cliff. They tell us that it takes 4 seconds to hit the ground. They also give us this horizontal velocity, but remember, that does not matter. The time and the height are going to be related to each other. So those are the only terms I'm going to look for. Essentially, I'm going to do I could do the XY column, but I'd only be focusing on the Y column. since the x doesn't really factor in here. So I'm going to use the knowing x equation again. So the final position is going to be 0, 0. The initial position is what I'm looking for. Because it's being thrown horizontally, the initial velocity in the y direction, is 0. So plus 1/2 a t squared. So we end up having that x naught is going to be equal to 5 times 16, which is going to be equal to 80 meters. All right. Here's the next one. Oh, pause the video yourself and we'll go over in a second. All right. So this one's also one that's, for the most part, pretty straightforward. Fully conceptual. They want us to figure out how the horizontal velocity at point A compares to point B. Once again, the acceleration in the x direction is 0. That means that the horizontal velocity does not change as it falls through, so it is going to be the same throughout. All right, here's the next one. Pause video, work self, and we'll go over in a second. All right, so for this question, they tell us the vertical component of the velocity, and they say that it lands at the same height, and they want the total time it's in the air. So what I'm going to do is the knowing x equation. Both the initial and final positions are going to be 0. And then the initial velocity is this 15, looking for that time, plus 1/2 a t squared. Move things around, do some basic algebra. We get 5t squared equals 15t. Divide 5t from both sides. And I get t equals 3. Now, there's no number that's exactly 3. That's because this equation, this problem probably used 9.8 instead of 10. It's fine. You just look for the one that's closest to 3. And that's it. All right, here's the next one. Pause the video, work self, and we'll go over in a second. All right, so this one's a little bit trickier as far as how to approach it. There's a variety of different ways to approach it. I'm going to show well, you know what? I'm going to show 2 ways. I'm going to show the longer way first. So they want to figure out how high the person jumps, and they tell us that the person's in the air for 0.8 seconds. So that 0.8 seconds is referring to the person going up and down. So one way I could do this is I can use this 0.8 seconds to figure out what the initial velocity was of this entire setup. Um, that could be done in a variety of different ways. I could do that with the knowing x equation. So you know what? I'll do that. So the final position 0, the initial position 0. I'm looking for the initial velocity. The total time is 0.8 seconds plus 1/2 -10 0.8 squared. I can actually divide a 0.8 from both these terms since over here it's going to be 0. So we end up having 5 times 0.8 equals v naught, 4 meters per second. Now that I know the initial velocity, I could do either the knowing x again, this time changing the time to be 0.4 to say that it takes 0.4 seconds to reach that maximum height. I'll explain that in a little bit more detail later. But I can use this initial speed to figure out what the final maximum height is, or I can use the timeless. So I'm actually going to do that one instead. So at the maximum height, where we want to try and find the highest height, the final velocity is going to be 0. So 0 squared equals 4 squared plus 2a, and then we're looking for that maximum height. So moving things around, we end up having that delta x is going to be equal to 16 divided by 20, which is 0.8. Now, I said before that there was another way to go about it, and this one's a little bit more unique. So because of the fact that this is a symmetric projectile, in the sense that everything about it going up and coming down is equal. What do I mean by that? Well, as the person goes up, they are going to end up reaching some maximum height. The only acceleration they experience is that the acceleration of gravity pulling it down, and they go up to some height. When they come back down, they're going to end up falling the exact same distance and they're going to accelerate at the exact same rate going downward. So the distance that they traveled and the acceleration that they're traveling for is all going to be the same. So this entire projectile is going to be symmetric. What would be asymmetric if the projectile landed at a different height? So something like this, landing at a higher height or lower, or if there was air friction, because air friction would affect the acceleration as it goes up and down differently. So in this case, because it's a symmetric projectile, I know that it takes 0.4 seconds to go up to maximum height and 0.4 seconds to come down from maximum height. Again, because it's 0.8 altogether, everything's the same, so the time needs to be symmetric as well. With this knowledge, this means that uh, I could do what I did before, where I can treat this as the projectile going up to its maximum height, and that would change the time to be 0.4, but it requires me to know what the initial velocity is. So instead, I'm actually going to look at the second part, because what I can instead do is say, okay, well, this object is falling from maximum height when its velocity is 0 at that point. And I know it's going to take 0.4 seconds to fall from that maximum height. So what is that? So I can do that. Oh, sorry, 0 equals x naught. Need to get that in the correct order. So it's going to land at the ground. It's starting at that maximum height that we want to know. We know its initial velocity at that point is 0 because even though the initial velocity is referring to, like we normally think of it as starting at the beginning of the problem, in this case, I am focusing only on this later half of the problem. So it's 0 starting from here, and then the acceleration is going to be 1 half at squared. So we end up having x naught is going to be equal to 5 times 0.4 squared, which is equal to 0.8. So this is a nice little trick that you could do because of the symmetry in the projectile. All right, here's the next one. Pause the video, work yourself. I'm going in a second. All right, so this one's an easy one. It says that it ends up, they want to know the displacement of the ball when it's thrown to the point when it returns back to when it's thrown. So it's going from this point up and then straight back down and being caught here. It's the same location, so the displacement is going to be 0. All right, here's the next one. Pause the video, work itself. We'll go in a second. All right, now for maximum height questions, for the most part, they do give us enough information where any equation that has distance in it, I could use it to find the maximum height. But personally, I like using the timeless equation anytime we're doing max height stuff. However, we do no for this one actually we don't have to be careful. It's one that we're gonna have to worry about later on. So the final velocity is gonna end up being 0. The initial velocity is the 49 that we know, and then 2 times negative 10 times delta x. So I'm not going to use the time this time. I'm just doing this. So plugging in my numbers, we have 49 times 49 divided by 20, which gets us about 120, which is close enough to this answer. Because remember, most likely they're using acceleration to be 9.8. Right? So we're going to move on to 10. There you go. Pause video, work itself. I'm going in a second. All right, so they want us to figure out what the horizontal separation of the spheres are after 1.5 seconds. Now you might try to overthink this and treat this as two horizontal projectiles, but you don't have to even go that far, right? Because for the most part, the vertical direction has no effect on what's going on horizontally. So I can actually just pretend that this is two balls rolling on the floor with these speeds, and I'm asking what is the new separation after 1.5 seconds. After 1.5 seconds, this 30 meter per second object is going to end up traveling 45 meters. And after 1.5 seconds, this 10 meters is going to travel 15 meters. I'm just doing the speed times the time, nothing crazy. So that means they were initially 100 meters apart. This one moves 45 meters forward. The other one moves 15 meters forward. that is a total of 60 meters being barred in, leaving us with a new separation of 40. All right, because if we add up all these numbers, it would end up equaling to 100. So 40 meters is my distance. All right, here's the next one. Pause video, work itself, and we'll go in a second. Now, I apologize I wasn't able to show every single graph on here, but they want us to figure out what graph represents a ball being thrown upwards. One graph that I can immediately disregard is the fact this one, because our velocity graphs should not be curved. For the most part, velocity should be a linear line because we're only considering cases where acceleration is constant. So A is going to be thrown off. Now, there is another one that I'm going to end up getting rid of, but let's go through this conceptually. The ball is being thrown upwards, which means that it's going to be positive. They even say that that's the positive direction. So my velocity should start positive. D does not start in the positive direction, it starts at 0. So now we're down to B and C. Now, while it goes up, up, up into the air and it reaches that maximum height, that speed has decreased to 0. Unfortunately, both these graphs decrease to 0, so now we have to go to the next part. After that, it falls down. And by definition, when it comes down, it is no longer in the positive direction, which we already said was up, it's now in the negative direction. So the answer should be B, the only one that goes from positive to negative. Another way to think about this is that the acceleration the entire time is negative 10. This is the only one that has a constant slope of negative 10 throughout the entire trip. Even though the ball comes down and starts speeding up as it comes down, the acceleration is still in the other direction down. So this one wouldn't make sense. This might make sense if this was, instead of velocity, was speed. Now I have to write it on an angle. But if this was speed, then this would be the correct answer. And this should be the last one. So pause video, work itself, and we'll go over in a second. All right. They want us to figure out the horizontal velocity ball just before it hits the ground. Again, the acceleration in the x direction is 0. So that means this 20 meters per second doesn't change. So it's going to be 20 meters per second just before it hits the ground. And that's it. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.